In the previous video, we explored the world of reinforcement learning, a field where AI learns to make intelligent decisions on its own. But how does it know what actions to take? What enables it to learn from the environment? The answer lies in a fundamental model, MDP, Markov Decision Process, the backbone of all reinforcement learning algorithms. Let's break down its components one by one. The core components of an MDP: agent, the decision maker, the brain of the system; environment, the world in which the agent interacts; state, the information the agent perceives from the environment; action, the choices the agent can make to influence the state; reward, the feedback from the environment. Good actions receive high scores, while bad actions get penalized. Now, let's see how these components work together. The agent observes a state from the environment and selects an action to perform. This action affects the environment, causing a state transition. In response, the agent receives a new state and a reward, indicating the outcome of its action. This loop continues, allowing the agent to gradually learn the best way to act. Example 1. A robot navigating a maze. Imagine a robot lost in a maze. It starts at the entrance and must find its way out. The only way to succeed is through trial and error, learning from mistakes and gradually optimizing its actions. Agent, the robot; environment, the maze; state, the robot's current position; actions, move forward, move backward, turn left, turn right. When the robot takes an action, e.g., moving forward, it enters a new state and checks whether it has escaped. If it gets closer to the exit, it receives a positive reward. If it hits a dead end, it might receive a negative reward. Through repeated trials, the robot learns to navigate the maze efficiently. Here, the reward function is designed by us to teach the robot how to distinguish between good and bad states. The robot has no prior knowledge of the maze. It only relies on the reward signal to determine whether an action is beneficial or not. If an action moves the robot closer to the exit, we assign a high reward, encouraging it to continue in that direction. Conversely, if an action leads to a dead end, we assign a low or negative reward, discouraging it from repeating the mistake. Over time, the robot discovers the optimal strategy to escape the maze. Now, let's look at another classic reinforcement learning problem: CartPole. Imagine a pole balanced on a moving cart. The agent's goal is to prevent the pole from falling by controlling the cart's movement. Agent, the AI controlling the cart; environment, the system consisting of the cart and pole; state, the cart's position, velocity, and the pole's angle; actions, move the cart left or right; reward, based on how long the pole remains balanced, the longer it stays upright, the higher the reward. The learning process is similar to the maze example. The agent observes the current state of the pole. It chooses an action: move left or right. This action changes the state of the system. The agent receives a reward. If the pole remains balanced, it keeps earning points. If it falls, the reward decreases. One crucial aspect to note: the reward function is designed by us. The effectiveness of the learning process depends heavily on how well we define the reward. If the reward does not align with the desired goal, the agent may learn suboptimal behaviors. That's why reward design in reinforcement learning is an art. It requires careful tuning to ensure the agent learns the right objectives. We've explored the key components of reinforcement learning through two intuitive examples: the maze navigation and CartPole. The agent learns by interacting with the environment, receiving feedback, and optimizing its actions based on rewards. The key takeaway: rewards are not predefined, they are designed by us. A well-designed reward function is crucial for effective learning. In the next video, we'll dive deeper into cumulative rewards, policies, and value functions. Don't forget to like and subscribe so you won't miss it. See you soon.